All right, my hair is officially out of control. All right, so let us now kind of introduce the concept of the electric field, particularly looking at the electric fields for point charges. We're just kind of all the Coulomb's law sort of things we've been playing with, for a couple of lectures now. I feel like our vector abilities are improving. A lot of the math will be very, very similar to this, but with a slightly added abstraction on top of it. So, this idea of the electric field, conceptually, again, the point is that we're getting to a way to describe how I could have, say, an electron here, and yet the rest of the universe knows that the electron is there without it having to go and touch the electron. So if I had another electron nearby, it would know to repel itself and try to get away. There would be some sort of force that acts on that second electron that pushes it away, even though the two electrons themselves are not touching. This action at a distance, again, was very weird for people when we were first studying these things. Now we can describe it in terms of the concept of a field, namely the electric field. Now I will say, if you then ask me what's a field, we really do not have a great answer to that, right? These are still kind of modern ideas of us trying to, of just what is a field. But it nonetheless is going to give us a way to quantitatively describe how you can have action at a distance in the case of charges. Though you could, again, use the same sort of idea with, say, gravity as well. Gravity pulls on this pen, even though it is not touching the pen, through the presence of a gravitational field that tells the pen how to react in the presence of the Earth. Tells the pen that when it's released, it will feel force, and as a result have an acceleration that goes towards the center. Let me see if I can motivate this with a simple example. Suppose I have some charge Q, and then there are two other nearby charges. There's going to be some charge here, which I'm going to call Q1. There's going to be some charge down here, which I'm going to call Q2. I don't really care whether they're positive or negative. We're just going to write this down kind of abstractly and mathematically. And I want to know what is the net force on Q. So the question then is, what is F net on big Q? Well, at this point, hopefully, we're getting pretty good at calculating what this should be. There's this Q1 charge, which, if I want, I can draw this vector here, which corresponds to the vector that points to capital Q from Q1. There's also this vector here, which I could calculate, which points to capital Q from Q2. Give me those vectors. I can then calculate their magnitude. I can then calculate the unit vector corresponding to them. And I could write down that F net in this case looks like it's going to be F on big Q from Q1 plus F on big Q from Q2. And then let's write this out. Right, so that looks like it's going to be K big Q, Q1, all over the length of R, Q, Q1, all squared, multiplied by the unit vector that points to big Q from Q1. Add to that K, big Q, Q2, divided by the distance between big Q and Q2, squared, all multiplied by the unit vector that points to big Q from Q2. That then gives me, as a vector expression, the net force. Let me factor out that capital Q. So I'm going to write this instead as big Q, and this big bracket that's going to be kind of K, Q1, all over R, Q, Q1 squared, times the unit vector big Q, Q1, plus K, Q2, all over the magnitude R, Q, Q2 squared, multiplied by its unit vector, Q, Q2. if I'm calculating the net force on capital Q, right? There's some charge, capital Q, and I want to figure out what is the net force it feels. It feels a force from the other two charges, which reach across space, action at a distance, and decide whether to push or pull that charge, depending on if they're the same sign or opposite signs. So, in kind of studying, right, in focusing on what's going on with capital Q, right, in focusing on the charge capital Q, it makes sense that the value of capital Q should matter in some way to determine the force. And there it is there. That's kind of the, I guess, inclusion of Q into the problem. Then there's all the stuff in brackets, which, if I think about it, really has nothing to do with capital Q. Maybe other than the relative location. All that stuff in brackets has to do with Q1 and kind of where Q1 is and what direction you would point in order to go from Q1 to capital Q. Then also the second term has to do essentially entirely with Q2. What's the charge on Q2? And then what direction, where is Q2 located relative to capital Q? That stuff is kind of telling you stuff that has to deal entirely with what's going on around capital Q. And then when you drop capital Q into that space, it then feels a force as a result of those two charges. We call this thing in brackets the electric field. In this case, really the net electric field. If you look at that thing in brackets, it is a vector. Right? There are two terms. Each of them has a vector associated with it. So the electric field is a vector. We usually write it as E, as a vector, capital E, with a vector sign. And it quantifies as a vector, so direction and magnitude. Kind of the presence of other charges outside of your system. If I want to see how capital Q responds to the presence of other charges, what I'm going to now restate this problem as is in order to calculate the net force on capital Q, I need to know the charge of capital Q as well as the net electric field acting on it. So we can also define the electric field. We can define it such that maybe I'll indent this and bracket this, right? That the force on capital Q from all other charges giant subscript is equal to Q times the electric field, which this electric field is defined by all other charges. capital Q does not enter into that definition at all. It only has to deal with, you have to use the problem above, Q1 and Q2. The electric field, right, it's a vector at each point in space. Right, so we may call that a vector field. The units, not too bad to work out. I know if I take E and I multiply it by Q, which is a charge which has a unit of Coulomb in SI, I need to get a force, which has a unit of Newton. So the electric field better have a unit of Newtons over Coulomb. When I multiply it by Q, the Coulombs cancel, I get a force. So that's kind of worth a highlight. Right, E does not depend on capital Q at all. It depends on all the other charges that are in the system, or in the problem rather, such that when you drop capital Q into the system, into the problem, you can calculate the force on Q by this expression. And this is probably best represented with some kind of pictorial examples. So you, I imagine, have played around with this in lab already. But you can imagine, if I have some positive charge and I place it there, I could ask if I were to roam around, maybe my sensors here, if I were to kind of hang around here, how do I know whether or not I should be, repelled or attracted to this object? Well, we can think of that this charge creates an electric field, that it sends out a message to all other points in space saying, hey, there's a positive charge nearby, right? So if you're positive, go away. If you're negative, come on over. And as I move this charge around, right, these vectors kind of change in order to kind of quantify both in direction, which is the direction of the arrow, and magnitude, which I think has to do with the brightness, right? It's brighter here and then gets dimmer over here. But again, if you go back to the expression that we'd written down using the kind of example to motivate, right, it seems like it depends both on, right, the charges themselves, and then as well as how far away you are from those particular charges. And you can get more fun and complicated with these things. So if I have, say, two positive charges and they're separated some distance, right? If I'm nearby this charge, it's saying that, you might expect that if you were some little, what we'll call a test particle, or particle that has a very small amount of positive charge. If I were to place it down in that area, big old force vector. That's saying, yeah, you want to get the heck away from this positive charge, right? If I imagine this yellow thing is a tiny little piece of positive charge. And as I go kind of farther away, that force changes. One, because it's getting farther away from this object. But then two, because it's also feeling a force, which is a vector, from this charge as well, which is going to be pointing kind of towards the upper left. So notice the arrow, especially if I go right here in the line of symmetry, notice here the net force seems to be pointing upward. Because you have a force vector that points kind of up and to the right from this charge, and you have a vector that points kind of up and to the left from this charge. Those components, the horizontal components, cancel, and then you only get kind of this vertical force. You can imagine going right down the center. It vanishes. That kind of makes sense. This vector, this charge is pushing towards the right. This vector is pushing toward, or this charge is pushing towards the left. As a net force of 0. Similarly, kind of down here, you can kind of see how this can play around with both a magnitude and direction. But of course, we can get more fun, right? Put a negative charge here. Make a sign that looks like that. Now you have 3 charges that are making their presence known. So that if I was a little particle here, kind of hanging out here, seems like if I'm a little piece of positive charge, right, I'm feeling myself repelled here, repelled by this one, that's far away, but then attracted by this one, and it seems like the net is that I'm kind of going up and to the right. Versus if I'm kind of over here, kind of closer to the negative charge, I feel a big ol' force attracting myself. This is repelling me kind of in the same direction towards the negative charge. And this one's kind of changing my direction a little bit. You can see, you can find those interesting spots like here's where they all seem to be perfectly balance each other out. Right, I got a negative charge pulling this thing up, but then I got two positives kind of pushing it to the right and down, and here to the left and down. The horizontal components vanish, but then the vertical component kind of is perfectly balanced by the upward pull from this. So what are these arrows and where are they coming from? Again, this is a way that we are quantifying the electric field, which the way you do it is, and again, all the math I've written down kind of does this naturally for you, but we'll be a little bit, well, I'll reiterate that with a quantitative example in a second, is that these vectors, right, that quantify the electric field, notice that these vectors are defined everywhere in space. In this kind of 2D example. Everywhere, let's even take some of the charges away. Let's take that charge away and that charge away. So I have a positive charge right here. Now, everywhere in space, there is a vector I can write down that is the electric field, the vector that is associated with this positive charge that lets the rest of the universe know that that positive charge is there. The magnitude and direction of that arrow quantifies how much charge is here and how far away you are from it, so that if you're all the way out here, you can't really see it, tiny little arrow, right? That's kind of telling you kind of what direction. It's telling you that there's a positive charge over here, so that if I'm positive, let me move it closer so we can see the arrow. It tells you, right, the direction of the electric field, the kind of convention is the arrows point as if you were to drop a tiny little positive charge in, and then that arrow tells you the direction you would of the force vector on you. So again, this is a positive charge. If this yellow dot were also a positive charge, I would feel a repelling force. In what direction? That's the red arrow. With what magnitude? Well, then I have to crunch the numbers, the KQQ, over the distance between these two dots squared. But I can, even if I don't know the charge on the yellow dot, talk about this thing called the electric field, right? Which is just essentially KQ of that charge divided by the distance to whatever point you're interested in. It's defined everywhere in space. And we'll play around with this for a couple lectures, but again, the convention is that these arrows kind of point in the direction that the force would be if your kind of little pretend test charge were itself positive. So again, if this is a positive charge, if this yellow dot were positive, right, I would feel them being repelled. I replace this with, say, a negative charge, right? Again, if the convention is that your test charge is a tiny little piece of positive charge, you would feel it being attracted towards this negative charge. So the electric field points towards negative charges and away from positive charges. Here's kind of an example. This might be a nice example of what's called a dipole. You have a positive charge and a negative charge. Notice the direction of the electric field goes away from positive and towards negative. And again, that's the direction that the force vector would point if you were to place a tiny little test charge anywhere kind of in the vicinity. What force would it feel as it were, depending on where it's located? And you can see the direction changes as well as the magnitude, right? Really strong, it's weaker, 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 weaker. And then where it points also depends on where it is relative to the pluses, the positive and negative charge. And then of course you can get, really funky. Add some charges, a complicated charge distribution. And you can imagine kind of playing this game where you could calculate the net electric field at any point in space, which would just be the contributions from each of these individual point charges. This is kind of a 2D example. Of course, this really happens in 3 dimensions as well. Here's kind of an example of if you had a positive charge, what electric field does it have? Here's kind of a 3D representation where the arrows are showing you the electric field. Right, if I were to drop down anywhere in this box and I were a little positive charge, I would feel myself kind of being pushed away from this charge. You can imagine I think they have a couple examples, right? A dipole. So I have kind of, this one is positive, this one is negative, and you kind of can see in 3 dimensions kind of what's going on. Not all dimensions are symmetric, which makes it a little bit harder to visualize. And we'll be working towards other cases where it's not just point particles, but it might be, a line of charge, right? So, think of a wire or something like that, and what's going on there. It seems like all the arrows, well, it seems like that's negative. Let's do a line of positive charge. Right, then kind of can see all the arrows. Seems like there is some symmetry going on that we'll have to think about kind of what's going on there, for this particular line of charge. It's kind of fun to visualize. All right, but let's write down for posterity some of the things I just said. So the direction of the electric field points away from positive charges and towards negative charges. And you can do this by imagining placing a test charge. So imagine placing what's called a test charge, which is an absurdly small but positive charge. I'll elaborate on what that means in a second. Right, so you place an absurdly small but positive charge and kind of monitor the direction of the resulting force vector. That then tells you the direction of the E field. So again, if I take some charge here, let's say it's plus E, I think it's a proton. Right, I can imagine placing a little test charge, say here, that little red dot I just made on the screen. And again, the idea of them calling it, they really don't use this notation as much anymore, so don't worry too much about this. But essentially the idea is that, if I placed a giant ball of charge at that point, you might imagine it would start to rearrange all the other charges. The idea here is that we're just we don't want to disturb the charges that are already there. We just kind of want to see, what would go on if I were to place a charge at that point. Right, so I can imagine if that little red dot were a tiny, a positive charge, I would expect the force to point kind of in this direction. So then we say that's the direction of the E field at that point. If I were right here, very close to the positive charge, I can imagine if I were to put another little tiny positive charge there, I'd probably get a big old force vector that would point to the left. So that's the direction of the E field there. And if I'm here, right, you can imagine then kind of drawing out, kind of picking any random location in space. It's not a very good arrow. And you can imagine kind of tracing out the direction. And if we're careful, we can also quantify with the magnitude, the length of the arrow of the electric field. Again, points in the direction that a positive test charge would experience. So then similarly, there's another charge here. It's negative E. Then I place a test charge here. I can imagine if I put a positive charge at that red point, what direction would the force vector point? Well, if it's positive, it should be attracted to this E. So then that would be the direction of the force vector. If it's here, imagine it be directed towards there. Here, that way, not as strong, it's farther away. Here, kind of is all pointing radially towards the negative charge. These are arrows, and I'm trying to give I'm trying to quantify it a little bit by the length of the arrow, so it has both a direction and a magnitude, right? This is a vector quantity. These arrows, the E field, right, is being shown by these arrows. Again, it is letting you know kind of how those charges let their presence be known, so that when you put another charge around, we know how that particular charge will react as a result. So if I look at, for say, a point charge, right, so again, let's stick with, we have some charge here, and it has some charge Q. Say Q to be positive for right now. I were to place some test charge here, right, which I'll call it little q. The force kind of on little q from big Q would be kind of K, little q, big Q, over the distance between them squared, right? A vector that points to little q from big Q squared, multiplied by a unit vector that points to little q from big Q. All right, just to draw it out, right, there's some vector here, R, to little q from big Q. And if little q we take to be positive, right, and capital Q is also positive, right, we know then that this force vector kind of also points in the same direction, radially away, right? It points in the direction, pointing away from capital Q. This would be kind of the force on little q from big Q. And again, like what we did before, if we factor out that little q, looks like then we have K, Q, this distance squared in the denominator, and then the directionality, because this is indeed a vector. This thing in brackets we define as the electric field for a point charge. Something that kind of points radially away, right? It points in the direction, right, that gets you as far away from the charge as possible. And notice that the direction of this vector that I've highlighted also kind of, the math, does the right thing, like what I said before, where arrows go away from positive and towards negative, right? If capital Q is positive, this entire thing is positive, and this thing points away from big Q. If big Q itself was negative, then this thing would have an overall minus sign there. So this thing would point not away from Q, but it would point towards big Q. So the math gets the directionality right, depending on if the charge is positive or negative. And again, we will build in sophistication as we kind of work this up. And essentially, it's the same math as what we did before. We're just separating this component, which we're now going to call the electric field, from the charge of interest. So let's do kind of one very simple example, just so that we have enough to work from when we do problems in class. Let me throw down some axes. And suppose there's a charge on the x-axis, let's call it Q1, and it has a charge that is plus E. And then there's another charge up here, Q2, which has a charge of negative E. Let's say they're both a distance d away from the origin. And the question is, what is the electric field vector at the origin? Again, with the idea that if I were to place a small positive charge at the origin, what would be the direction of the force vector? And then we're going to take away the that test charge and look at just kind of what is the presence of these two charges at the origin. Well, we could always be qualitative. It's always going to be qualitative first, right? Imagine I put a positive charge at the origin. Well, I know Q1 is going to want to repel it, so that Q1 will probably will point it that way. Not probably, it will, right? On the origin, kind of from Q1. Then Q2, if I were to place a positive charge at the origin, it would want to attract. So then there's going to be, I'll do a different color, another force vector here, which that's going to be the force kind of on the origin from Q2, or on a hypothetical positive charge at the origin. So that looks like the net vector. It's getting a little busy. Get rid of this D. So that looks like the net vector, if I add that blue and the red together, it's probably going to be something like this. Right, F net. And so then that is what we say is the direction of the electric field. But now we want to calculate the electric field quantitatively. So the way I like to write the electric field is, let's write it like this. The electric field, at a point from a charge Q is going to be K Q divided by this vector R squared times a unit vector R. Let's define R, where R in this case is a vector pointing to the point of interest from the charge Q. Which might sound very familiar, right? If there were a charge at that point of interest, right, this would be the same vector we were calculating to calculate, a Coulomb law force. So now let's look at for the problem above. Let's take Q1 first. So the point of interest, which I'm going to use maybe I'll use I for, the kind of the vector pointing to the location of interest. Well, the location of interest is the origin, so that's just going to be 0, 0. Then Q sub 1, the position of Q sub 1 looks like it's negative d in the x direction, 0 in the y direction. It's on the horizontal axis. It has no vertical position. And so then the position vector that points to the location of interest from Q sub 1 looks like it's, by definition, R sub I minus R sub Q1, or that's just D0. Points to the right and doesn't point vertically at all. Makes sense? Again, we'll go fast on this because you can convince yourself or pause the video. The magnitude of this vector is just D. So then the unit vector that points to the point of interest, the origin, from q sub 1 looks like it's just 1, 0. Or just x hat, or I, if you're using the engineering notation. So then the electric field at the point of interest from q sub 1 looks like it's then k times q sub 1 divided by this vector that we just calculated squared that points from the charge to the point of interest multiplied by the unit vector that points to the point of interest from q sub 1. Looks like it's k positive e divided by d squared. Then this is a vector that looks like it was just 1, 0. This is the vector for the electric field that is coming from that charge on the left, right? That charge on the left makes its presence be known everywhere in space, particularly at the origin. We could write down that the electric field is a vector that has this magnitude, ke over d squared, and it points in this particular direction, namely to the right. Right, this looks like a vector that points to the right. E at the origin from Q1. Which again, if I were to put a tiny little positive test charge at the origin, the force on that little charge would point to the right. That is the direction of the E field. Then similarly, E at the point of interest from Q sub 2 needs, looks like then it would be kind of k q sub 2, the distance from to the point of interest from q sub 2 squared, all multiplied by the unit vector that points to the point of interest, the origin, from q sub 2. Then that looks like it's k negative e over, it's also a distance d squared, and a vector that points to the origin from the top charge, looks like that's 0, negative 1. And again, go through the steps explicitly, right? Write down the position vectors for the charge in the point of interest, figure out that relative vector, what I'm calling r sub iq2, figure out its magnitude, calculate its unit vector, convince yourself this is what you get. So then if I multiply that negative sign in, looks like it's k e d squared, 0, positive 1. A vector that seems to point straight up is the electric field at the origin because of q sub 2. Which again, that direction matches the direction of the force. If I were to put a tiny little positive charge at the origin, it would feel itself pulled upwards towards the negative. So I expect the electric field to point upward. Then E net, just the sum of the two. So it looks like it's ke over d squared, 1, 1, when I add the two vectors together. And indeed, that looks like it is a vector. If I redraw my axes, there's a charge here, E, the charge here, negative E. The net electric field seems like it points at a 45-degree angle at the origin. That has a magnitude of ke over d squared. Well, no, because that 1, comma 1 is not a unit vector, so its magnitude is not quite that. It's square root of 2 times that. But at least this tells me the direction. Since I said it out loud, we might as well do this, right? What is E net the magnitude? Well, then that looks like it's just the square root of ke over d squared squared plus then the y component ke over d squared squared. Those are both the same, so it looks like it's just square root of 2 ke over d squared squared, or that's just square root of 2 times ke over d squared. So the length of the vector is square root of 2 times that stuff in parentheses. The direction looks like it's, to the right and up. So again, very similar math, but we're just abstracting a little bit of thinking about, if I want to study a particle that's at the origin, how does the rest of the charges let themselves be known, right? That is the electric field. And essentially, it's the same exact sort of math. We just don't have we don't have a number for the charge at the origin. All right, we'll build off this. And again, this was kind of a very brief intro, but allows us to do some problems, because I think when we start plugging in some numbers and actually do some calculations, that's where we'll actually start to get a feel for this somewhat abstract idea. So we'll start there in class.